Okay, so the tests are graded. I'm just going through, like, filling out the rest of the grade book of the grades I have to take. Talk to the TAs about getting your labs back a little bit sooner, trying to get them to push through and get some more grades on the labs, and then I'll enter in all the attendance and all that stuff. So I'll update the letter grade too. After every exam, I update the letter grade. So sometimes if your letter grade doesn't change, and Blackboard shows the last update of your letter grade was like September 17th or something crazy like that, but it's always updated after every exam. If it hadn't changed, it won't show an update. It only shows an update if there's a change on Blackboard, but I promise you I've uploaded all of the letter grades after each exam. Okay, so today we're going to be talking about quantized electron wave functions. So we've moved from sort of the theoretical one-dimensional particle in a box, which was an electron on a wire. Then we got into real molecules and we talked about rotation. So that was the smallest energy changes. So that's, very, very small. And the wavelengths associated with those are in the microwave region. So millimeter wavelengths of light interacting with rotational wave functions. And then we get into the infrared, which is the vibrations of the molecule. And those would be a little bit larger. So we're talking about wavelengths that are absorbed there in the infrared light, which is micron. So we went from millimeters to microns, and now we're in the electronic wave functions. So the electrons around an atom, we'll start with atoms, and then we'll get to molecules. Okay, so today we're going to start the very beginning of the atomic wave functions and energy differences there in the visible region, which are in the nanometers, so even smaller. So nanometers, energy differences, that's the wavelength for the energy differences in electronic spectroscopy. Then we get to microns, a lot longer wavelength for vibrations, and then millimeter wavelengths for rotations of the molecule. Maybe you're thinking, what about translations? Well, they're so close together, we don't have a spectroscopic technique that can measure those small energy differences. So that's pretty interesting. So we do verify that the translational motion is quantized by using statistics and statistical thermodynamics. And so we'll get that in the second semester. So that's the first section of the second semester, is looking at the theory behind whole molecule motions, like a gas, and those gas velocities, and how that matches thermodynamics if you take a quantum view of thermodynamics. That was actually the thing that convinced Einstein that quantum mechanics was real. He thought it was just a mathematical trick, that it was working for spectroscopy. But thermodynamics had built the Industrial Revolution. So that was real science. Like we're building bridges and smelting iron and doing all these things with thermodynamics, and steam trains, all of that's thermodynamics. So they had revolutionized the world with thermodynamics. Quantum mechanics was brand new in the 1900s. And so Einstein was like, this statistical view of thermodynamics, that's where his famous quote, "I don't believe God plays dice with the universe," because it was a statistical view of atoms, ions, and molecules that led to the thermodynamic theory. That is sort of a quantum view of thermodynamics that Einstein was skeptical at first, and then he embraced it. So let's jump into electronic motion and wave functions. So let's talk about the easiest atom. Let's start with hydrogen. So the hydrogen atom's electronic structure, you have this potential energy term, the Hamiltonian, and the Schrodinger equation. So what is a potential energy term? Well, we kind of covered this a little bit with the Gaussian. When we got into Gaussian, we went from the particle in a 1D box Hamiltonian to the molecular Hamiltonian, or the atomic Hamiltonian. And so again, those potential energy terms are the Coulombic attraction of the electron to the nucleus. And of course, the mass of the particle comes in on the Hamiltonian piece in this reduced mass piece here. So for a hydrogenic atom, it's going to be the mass of the electron right here, and the mass of the proton. And of course, if 1 over the reduced mass is equal to the sum of those, this mass of the electron is 1,000 times smaller than the proton, so that's the largest number. You're dividing by the smallest number, so that means that's the largest number. So that's going to be essentially the reduced mass is close to the mass of the electron. So that helps simplify the mass. The math is just using the mass of the electron in this equation. So the Schrodinger equation for this molecule has got the Hamiltonian piece here, which contains the kinetic energy and the potential energy terms, times the wave function, and that eigenvalue equation gives us the energies. So what about these wave functions? Well, that's what we're going to be talking about today, is the wave function for the electron around the atom. Now, the analytical solutions, like you did in a particle in a 1D box, that's where you just start with the calculus and you do these derivatives and everything like that by hand. That can be done for the hydrogen atom. It's incredibly tedious. It really would. I think when we did this homework in graduate school, we solved for the energies of the hydrogen atom, and it would take up this whole board. Writing, your variables about that size. So pretty small writing would fill this whole board. So I think it would probably take me 2 lectures to go through, and I think you guys would be asleep by the end of it. Okay. And so that's why I don't go through it, because I'm not going to require you to do it. Okay. But you can see it online. So if you're really curious, look at the solution of the hydrogenic energy equation, and I'm sure there's a video out there. Okay, but there's 3 things that emerge from these wave functions, right? A wave function has to be, we can go through it, normalized, orthogonal, it's got to be continuous, it's got to have a continuous first derivative, and it's got to have boundary conditions where it goes to 0 at the boundaries, and it's got to be non-zero in the middle, but it can't be infinity. So all of these restrictions on the wave functions, these are what we have, and so it's also got to be quantized. There has to be a quantum number. So these are the quantum numbers for the electronic wave functions. There's N, L, and M sub L. So those are your quantum numbers. There's gaps in your homework for that. Okay, so the N, look where it is. This wave function is broken into 2 pieces, the spherical harmonics piece and the radial distribution piece. Think of, I don't know how good you guys are with thinking about spherical polar coordinates. Did you ever come across those in your algebra or whatever, all through high school, or maybe even in calculus? Normally I'm talking about X, Y, and Z, right? When I'm talking about our 3 degrees of freedom. Every particle in the world, in the universe, has 3 degrees of freedom for translation, X, Y, and Z. But it's not always convenient to use the Cartesian coordinates. So think about the Earth, actually. What's the best place to find the location of this building on Earth? It's not X, Y, and Z from the center of the Earth. Okay. It's longitude and latitude, and those are the angular momentum functions, theta and phi. What would R be from the Earth center? Yeah, the distance from the center, and we have a word for that too. Altitude, right? So that would tell me not just where I am in the building, but what floor I'm on. Okay, so if you want to locate me, you need to give me the longitude, latitude, and the altitude, or depth. So we have it relative to sea level. That's a fairly stable elevation or radius from the Earth's center is sea level. And so whether we're above sea level or below sea level by a certain number of meters, that's our radial position. And then longitude and latitude is our angular position relative to the North Pole and the prime meridian. So there's a line that goes, I think, through Greenwich, England, and that's the 0, and that tells us the longitude. Okay. Now, how do you remember which is which? So this is just an aside. So longitude has the word long in it. That's how far you've gone. And it's a naval thing, right? So you're going away from England across the ocean. Okay. Longitude is how far you've gone, and latitude is how far left or right you've gone relative to the North Pole. So that's the way you know it. So longitude is the going around the Earth, like Magellan, okay? And latitude is how far from the North Pole you are. So then after you do that Schrodinger equation, you get these energies out. So this orange curve is just kind of showing you the edge of that orange curve is the potential energy. So this line right here is the potential energy. It goes to minus infinity as the electron and the proton actually touch. If they were able to touch, they would merge together, and you would actually have electron capture by the proton, and that proton plus an electron would turn into a neutron. Okay, that doesn't happen for hydrogen, but it does happen for the uranium elements, all the radioactive elements, the really, really big ones that have 1s electrons that are so close to the nucleus. On occasion, one of those electrons will get sucked into the nucleus, and it'll turn that proton into a neutron. And now the identity element changes. So if we lose a proton, what happens in the periodic table? If the element moves one to the left, right? Because you look at the protons. So we don't get to that till the end of thermodynamics. So if you stay in thermodynamics in the spring, the last fifth of the course is nuclear chemistry, where we start seeing elements hop all over the periodic table. It's really cool. Okay, but at this point, this 1s electron gets this close to the nucleus right here, and it has that potential energy. Because it's really close to the nucleus, then it's really low in energy. So that's the lowest energy. So all our energies are negative. So this principal quantum number n tells you how close you are to the nucleus. That's that radial distribution function. And even though L is present, L is that angular momentum quantum number. Yes?
Can you point out one more time where you're saying that that's like the margin of where it is before it becomes a neutron? Like, was it underneath?
Yeah, it's way down here. So they're not really touching here. So the electron is still out of the nucleus here.
Okay.
Yeah. And this is showing the 1s electron wave function right here. This red curve is actually R of n, the radial distribution function part of psi. So I'll do this. It's a function of R. So that's the radial distribution function. Some parts of the notes just call it psi n of R. Okay. That's an or. So it's Rn of R or psi n of R. And notice how it doesn't quite stop right there where the potential energy curve, is. It goes sort of into that potential energy curve region a little bit. Okay. So if you wanted to pick like the 95% confidence interval, if you squared that radius, that wave function, it would be in this region. So that would be the region in which the electron oscillates around the nucleus. Okay, so about that far. But notice that the 2s goes even further, and the 3s goes even further. And so we'll look at those curves in a minute. Now there is an angular quantum number, L and M sub L, but they're not in the energy equation for the one electron wave function. So that's a blank in your notes. I looked at the notes last night and re-uploaded them, so I'm fresh on my mind about where the blanks are. But the L and M sub L show up again, or at least L does, in the multi-electron atoms. So everything above hydrogen has multiple electrons, and we have electron correlation. And so that changes some things. Okay. So helium, we can solve the hydrogen atom wave function and energies analytically. Just when we get to helium, we can't. So like we got analytical solutions for one atom on the periodic table. And that was what Dirac was saying. We know the equations, but we have no way to solve them. Like we can write out the Hamiltonian for helium, but that electron correlation term doesn't have an analytical solution that we've discovered yet. Okay. So that's kind of interesting. Let's look at how the energy varies. Look how it's kind of similar to the particle in a box, but it looks upside down. Notice that n is up here in the numerator, n squared, and here in the hydrogen atoms, it's in the denominator. And the mass in the 1dPV is in the denominator, but here mass is this mu piece, and it's in the numerator. Okay, and so that's kind of interesting. But look here, this is negative. And so because the energies are negative, the same trends apply. So if you're looking at the particle in a box, when m gets big, it's in the denominator. So what happens to the energy? It goes down. Okay, but look at this. Mu is in the numerator. So when it gets big, it gets more negative. So the energy goes down. So the same trend that you learned with the particle in a box, these sort of trends that you've memorized, that if mass gets bigger, energies drop, happens also in the electronic wave function. So not sure how a mass of an electron could get bigger, but if it did, okay, let's say we made some other kind of thing where we had a proton orbiting some element, the proton cloud, it would be a much heavier particle, so those energies would be really, really low. Okay. And then as the quantum number goes up, okay, then this value gets smaller, but it's negative. So it gets less negative. So the energy is going up. So that's the same thing we saw with the particle in a box. As quantum number went up, the energy went up. Here it becomes less negative, so it's still going up. So we see the quantum number here. This is n equals 1 quantum number, n equals 2, n equals 3. See, it goes up, and you see it doesn't go up as much, and so it's like an inverse relationship to n squared. And then as nuclear charge goes up, then the energy goes down. We don't have a corresponding version of nuclear charge in the particle in a 1D box, but we do have that in the hydrogenic energy level. Okay, let's look at this radial distribution function. This is what the wave function looks like. But look, if you look at it, it looks like it spends all its time in the nucleus at r equals 0. But this is the wave function. This is not the probability distribution. The probability distribution is the wave function squared. And you have to take into account the volume element. So we're no longer working in x, y, and z coordinates. We're working in r, theta, phi. And so when we integrate over all space, okay, what do we have to do? Well, we have to integrate the volumes. So as I go out in a particular angle, the volume is huge, way far away from the nucleus. But as I go in with the smaller and smaller r's, that angle is the same, but the volume that it encompasses gets incredibly small. In fact, it goes to 0. So the volume element goes to 0 as r goes to 0, and that's why we end up with the wave function being pinned back down to 0. You see an r squared term, this r squared volume element causes the wave function to drop to 0 at r equals 0. That's what, that's another way to say the reason the electron stays out of the nucleus is there's no volume there. It's like it's trying to put it in a smaller and smaller space, and it just won't fit. It's not exactly the way to say it. It's a wave function, but it's a good way to think about it in terms of the problem. And so what this does is this sets up our wave function to where it's 0 at the origin, and it's 0 at infinity, and it oscillates in the middle. So that's what makes it a valid wave function. It's not like the particle in a box. The boundary conditions for the particle in a box were that at the left and right side of the box, the potential energy went to infinity. And so it didn't have infinite energy, so the wave function had to go to 0 at the boundaries. Well, here we don't have that. We've got actually the potential being lowest at the nucleus and 0 at infinity, but the volume element goes to 0 at the nucleus. And then the wave function, it's like a string. If you were to dangle a string like this, you could get it to move here, but if the string was infinitely long, the bottom of the string would never move. So you would move here like that dramatically because that's real close to where you're shaking it, but at the far end it would never move. And that's what these wave functions look like. In fact, you could model them with the functions of an oscillating string, where you're oscillating at one end but letting the other end hang. And so that's what these wave functions look like. So they get more gradually sloped as farther away from the nucleus. So let's look at the sizes of these elements. So my kids and I were walking by Target one day, and I noticed that big red ball in front of Target. And so I got to thinking scientifically, and they were rolling their eyes as they do. And I said, what if that ball is about 1 meter across, was the proton? Where would the electron cloud be for a hydrogen atom? 71? 71, 72. I put 71. I looked at it, the math, and maybe we're off. At least to one significant figure would be 70 miles. So that's pretty big for the hydrogen atom. So that goes all the way over to Shepherd, Livingston. I don't know if you're from this area, but almost all the way to Spring, Navasota. Doesn't quite make it to College Station. Okay, Madisonville, Lovelady, Groveton. So that's a pretty big area. So when we say that the material is mostly space, it's true. All of the mass of the hydrogen atom is in the proton. So the electron is taking up a lot of space. It's 1/1000th of the mass of the proton. And so it's mostly space. That one electron is covering that whole area. In fact, don't think of it as a particle zooming around. It's a cloud that's oscillating. That electron is sort of smeared over that whole area. So if you're thinking of it as a particle, it's hard to conceive of that, right? But if we were to shoot something that was small enough, if we had a spoon small enough that would sample here or sample there, we might get an electron. And you could calculate the probability of getting an electron, and that would be the wave function squared. And there would be, again, this would be the most probable place to find it, is out here at this edge of that circle. So if that's a 1 meter ball here, it's actually 2.4 times 10 to the minus 15 meters. Remember, 10 to the minus 10 is an angstrom. And so this is 0.000025 angstroms. So that's really small. Okay? But if it was as big as a meter, then the hydrogen atom would be 71 miles across. And that's that most probable. So that's the maximum of this probability distribution function, the wave function squared. So notice if I were to do the 95% confidence interval, it'd be about 2 or 3 times that. So it might be 210 miles across to get the 95% radius. Well, what about a sodium atom? So it's about 3 meters across. Okay, it's got 23 particles in the nucleus. So it's got 11 protons and what would be that? Maybe 12 neutrons. And so this would be the most probable radius for this sodium atom would be that 3s radius there, and that's 971 miles across. So that'll give you an idea visually of how big the atoms are on the periodic table. So if this is hydrogen, it's really a 4-county area in Texas. You've got over here, you've got San Jacinto, Montgomery, Grimes County, Walker County, most of Madison County. Okay, so 4.5 counties in Texas, and here would be the sodium atom. So it's about the size of Texas. So hydrogen, 4 counties near, in Texas, and the sodium atom is about the size of this whole state. Okay. So that should give you a sort of a feel for how reactive sodium is, because the reactions take place in the electrons. So if I'm coming towards Huntsville, and I'm still I'm over here in Carlsbad, New Mexico, right in the edge where Texas, meets New Mexico, I'm starting to interact with that 3s electron. Am I anywhere close to a hydrogen atom radius? Not even close. Okay, so reactions can take place a lot sooner and with less impact to the nucleus. Remember, this would be if the sodium nucleus was at target, and it would be 3 of those red balls in diameter, and yet its 1s electron is at Carlsbad, New Mexico. Is it going to notice if that 1s electron is stolen? No, not at all. So that tells you how easy it is to steal that electron from sodium. These are radial nodes in the wave function. We've gotten used to thinking in terms of nodes in like a one-dimensional wave function. So these are plotted along R, but you see, this is the wave function squared. Okay, so since it's squared, all the negative regions have become positive, right? So let's take this 1s. It might go up here and a positive, and then here it would be negative, and then here it would cross 0 and come positive again. So when we square it, this part became positive as well. Okay. But the zeros times zeros are going to be 0. So this still shows you the number of nodes we have. And you can see those radial nodes that I'm pointing out with these arrows. And this would be what a radial node looks like. And you can kind of see, I've tried to animate this, where the outer part of the cloud expands while the inner part of the cloud contracts. And then the inner part of the cloud expands while the outer part contracts. So going away from the nucleus, I'm trying to capture this this oscillation of these wave functions. You know, these parts are oscillating up and down here and here. Oops. So what does it mean for those things to oscillate? Well, these are it's a spherical shell. It's a spherical shell. So oscillation is like an expansion and a contraction. So becoming more dense or less dense. So if it expands, it becomes less dense. If it contracts, it becomes more dense. And so the electron density is increasing and decreasing inside this wave function as a function of distance from the nucleus. Okay, so that's, and then there's regions at that distance from the nucleus where it doesn't change, and that would be a node. Okay. So those are radial nodes. Notice there are no radial nodes in the 1s electron wave function. So the red one's the 1s, no radial nodes. So it's just a ball of electron density that expands or contracts, gets less dense or more dense. Okay, but then the 2s, there's one node. What do you think about the 3s? 2 nodes. 4s, 4 nodes, and so on, or 3 nodes, and then the 5s would be 4 nodes. So it just goes up with n-1 nodes for the s's. Okay, but then for the p orbitals, look at the 2p orbital. That's the first chance you get at a p orbital. And we'll understand what s and p mean in just a minute. But the 2s is the first p orbital, so they have 0 nodes. And then the 3p is the second possible p orbital, and it has 1 node. And so the very first time you have a particular orbital type, whether it be S or P or D, that very first one you get has 0 nodes. The next one has 1 node, the next one has 2 nodes, and so on, going all the way up. Okay, so let's look at these. So here we have the H atom wave function. We've looked at the radial distribution function. It's a 1D particle problem. But then we get to the spherical harmonics, and it's a little bit more difficult. But look, the clue to the spherical harmonics, the angular dependence, is that word, spherical harmonics. So think about if you have a spherical shell, and you can see a spherical shell when you blow bubbles. So that would be really fun. Next time well, it's Halloween. Maybe they'll have bubble things too in people's little candy, giveaways. If you get your hand on some soapy water and you blow some bubbles, right when the bubble detaches, you'll see it do stuff like this. And when it vibrates like that, that's a spherical harmonic. That YLM function describes every motion that sphere can take. And so down here in the bottom left corner, I'm showing one of the harmonic motions of a sphere. Oh, no. All right, here we go. See, it's orange, and then it's orange on that side. So what it's doing is this bubble is oscillating like this. Let's see, it's squeezing one way and then squeezing the other way. I can't do that with my hands. Let's see. Let's do it up. So it squeezes up, and then it squeezes down. It squeezes up, squeezes down. And the waist isn't moving. So notice this is moving left and right like that, but really just kind of bulging. The center of mass isn't moving, but the cloud is moving. It's bulging. And it's bulging in a particular direction. So this is what we would call a p orbital. And it's directional. And this is changing along the y-axis, so we would call that the py orbital. Does that make sense? Do these pictures now show, explain what's going on? If we were to plot the change, so if we just plotted the cloud, we would plot a sphere with some colors on it. But if we wanted to plot the change in terms of angle, let's pick an angle here from the z-axis. So we've got this angle here. Let's call this phi. So at phi equals 0, we're looking straight up at z. What is the change of that orbital there? It's 0. Okay, so we're going to plot the change as we go around, and this change is 0, so it's going to start at 0. So at this angle, notice the change is this small amount, and it's blue. Okay, and so we're going to plot a small amount, and we're going to color it blue. if we're right here, it's a bigger amount. It's still plotted blue. So we're going to plot that bigger. Here's the maximum change right here. So if we plot it along R, that's the maximum change. Look at what I'm plotting out. I'm plotting out this dumbbell shape. You see, as I go around this angle here and I plot the change in the cloud, I get this dumbbell shape. And if I go on to this side, so now I'm plotting this angle right here. So this is, again, phi has gone all the way around here. Now this amount of change is right there. And then I plot this, and it goes all the way around. This is the largest amount of change. And this, you know, these, let's say these numbers are negative and these numbers are positive. So we show that the large expansion, the orange part where it's expanding, we would call that positive. The blue part where it's contracting, we call that negative, and we plot the change. So it's the change in the spherical shape is what's being plotted right here. So this is, let's say again, this orange color is where it's expanding. So it's expanding along the y-axis and contracting at the negative y, and then sometime later it sloshes back because we can't have the thing translate. It's got to oscillate. It's a wave, it's oscillating. So sometime later it contracts on the positive y and expands on the negative y. So it's moving back and forth along the y-axis, and that's the py orbital. Now when we square that wave function, we're saying that wherever there's kinetic energy, that's the location of the particle. So this electron is moving back and forth along the y-axis. And so it can bond to things that are along the y-axis. And so the p orbitals give us directional bonding. The s orbitals give us omnidirectional bonding. But the p orbitals pick a particular direction. So px orbitals go along the x orbital, x-axis, py, pz. So that's what's going on with the spherical harmonics. These are the harmonic motions of a sphere. It would be great if we could have, I mean, I don't have access to this, but a high-speed camera and a spherical shell and a hammer. Where you can sit there and hang it from space, have a camera on there and bang it and watch it oscillate. And you would get all of these patterns. And if you could plot the changes in oscillation, you would get those exact pictures. So let's go through the quantum numbers and how we keep track of these things. So the principal quantum number starts at 1, not 0. So we got to keep track of which ones start at 1 and which ones start at 0. So particle in a box started at 1. Rotation started at 0. Vibration started at 0. But the principal quantum number for electronic motion around the nucleus starts at 1. And it goes up to infinity. So there's no limit on the principal quantum number. If it gets high enough, that electron will just leave the atom. Okay, so there is a practical limit, but in mathematical limit, there's no limit. Okay, this decides what shell it's in. So you have the 1 shell, the 2 shell, the 3, the 4, the 5, etc. So that's the shell. Then you have the angular momentum quantum number, and this is the shape of the orbital as you go around in longitude and latitude. L starts at 0. Okay? But it's bound, meaning it has a maximum value as n minus 1. So it can start at 0, and if n is 1, so you're in the 1 shell, that's all you've got for L, because 0 happens to be n minus 1. So, but then if n is 2, then you can go from 0 to 1 in L. And we have letters associated with this, because we have so many numbers, like sort of the address of an electron requires 4 numbers, and so what we're going to do is we're going to use the letters for L. So S, P, D, F are actually quantum numbers, corresponding to L equals 0, 1, 2, 3, and so on. And so for L equals 0, that's an S. For L equals 1 is a P, 2 is a D, 3 is an F. And that's all we have for the ground state orbitals on the periodic table. Okay, so we have the F block over here, cerium and thorium, the lanthanides and actinides. Okay, there are higher orbitals. We go to G and H and I, but those are for excited atoms. So you can excite an electron to a G orbital, which is a little weird, but we're going to learn about that in a couple of lectures. Okay. Then we have the magnetic quantum number. The reason it's called the magnetic quantum number is because we don't see energy differences in this one until we put it in a magnetic field. But this gives the position, the relative position of each orbital. So when I was talking about the px, the py, and the pz orbitals, those would be the m sub l, -1, 0, and +1. These go from -L, you can see the series there, from -L, so this is the minimum and the maximum. So from -L to L, and then with integer multiple or integer addition to each of those. So it might, if f is equal to 3, then it goes from -3, then -3 plus 1, which would be -2, -1 through 0, all the way up to 3. So it's bound by L. And then we have lastly the electron spin. So this is the spin of the electron, which is really an unfortunate term because mentally we think of an electron spinning like a little planet, okay, like Earth is orbiting the sun and it's spinning as well. And the reason that's irritating to scientists is because the electron's behaving like a wave. It's not a particle orbiting the nucleus, okay? But it has a tiny little magnetic moment. It has a little magnetic field. And that's what we're talking about this. It's called intrinsic angular momentum. If you have a particle that's spinning in space, it generates a magnetic field. It's the right-hand rule again. So if it's going in X and it turns to Y, which is what it has for spinning, then the magnetic field is on the where the thumb goes. So that's a spinning positive charge. So the right-hand rule is tied to positive charges. If it's a negative particle, it's the opposite. So this electron has intrinsic angular momentum, which means it has a tiny little magnetic field. And so that magnetic field corresponds to a spinning charge of a 0.15. 0.5. And so that's a plus or minus a half. It can spin up or it can spin down. And that's where we have the electron spin. So there's this Pauli exclusion principle that no two electrons can have the same 4 quantum numbers. So what this means is there's a maximum population of 2 electrons in each orbital. That's why this exclusion principle is why we can only put 2 electrons in each orbital, because you have 2 types of electrons, spin up and spin down. So the orbital is defined by n, L, and m sub L. So each orbital has those 3 quantum numbers, and then you can put 2 electrons in each of those orbitals. So this is where this designation comes from. The principal quantum number is this big number here in black, right? So all of these right here are the principal quantum numbers. So the 2s electron is in shell number 2, and the 4p electron is in shell number 4. So those are in. Then the angular momentum quantum number, L, is the p and the s and the d and the f. Those are the L quantum numbers. We can put, 2 electrons in a 4p0. Okay, so this would be the number of electrons in that type of orbital. If we don't specify the m sub L, we could have up to 4p6. Okay, but that's really the 4p -1 with 2 in it, the 4p0 with 2 in it, and the 4p plus 1 with 2 in it. So there's your 6 electrons because you have 3 p orbitals. Okay. And that's because the m sub L is bound by L, and if it's a p orbital, L is equal to 1, and so you have a -1, a 0, and a 1 for the m sub L. The m sub L tells you which type of orbital and specifically which sort of direction in space. It's very convenient for us to think in terms of Cartesian coordinates. So we talk about the px, py, and pz, but technically the x might be the m sub L -1, and the z might be m sub L equals 0, and the y might be m sub L plus 1. There's never a time when we have to specify which is which, so don't worry about that. Like, is m sub L -1 x or y? You won't ever have to know that. So let's look at the pictures. Again, these are the oscillations of the electron cloud, left and right, or forwards and back, or up and down, based on the X, Y, and Z. And those are your p orbitals. So it said we call them X, Y, and Z. So the X is the M sub L. And we don't really need to know which one is 0, which one is 1, and which one is -1. And here's the d orbitals. These are a little curious for you, I'm sure, because even if you did do these quantum numbers and things in Gen Chem, you probably didn't get into the designations of the d orbitals very much. Okay. And so there's 5 of those. Why is there 5? Well, L is equal to 2. So M sub L is equal to -2, -1, 0, 1, and 2. There's your 5. Okay. Now, again, it's convenient for us to think in terms of Cartesian coordinates, especially when we write out our structures and we put a Cartesian coordinate frame up there next to it. Now we can look at the orbitals in that molecule and on the atoms in that Cartesian system, and we can assign them different symmetries and so on. So we have this one, this XY. You see the XY, it's actually X times Y. That's the symmetry of the X-axis times the Y-axis. And so if I could plot this and look down on the XY plane, this is X, this is Y. So in this quadrant where I have X times Y, these are all positive numbers because I have positive X times positive Y. But over here I have negative X times positive Y. So all of those numbers are negative in that region. Down here, I have negative X times negative Y, so all of those numbers are positive. And then over here, I have positive X values multiplied by negative Y values, so that's negative. So you see this 4-quadrant plus minus oscillation. And that's how you determine that's an XY orbital. If you're looking in the XY plane and you see plus, minus, and so in this case, we've got this little blue thing is plus, this over here is plus, the oranges are minus. And so how would this look if this were oscillating? I'm going to draw a deformed electron cloud. So this is X, this is Y, and it would be bulging like this. Compare that to what a sphere would look like. You see how this wave function has bulged here and shrunk there and bulged there and shrunk there. So that's what the dxy orbital oscillation looks like. If you were to blow a bubble and you see it do this, that's the xy oscillation. Or it might do it like this at a different angle, and that would be a different set of planes, or maybe it does it forwards and backwards, and that would be another one. So we have 3 of those because we have 3 ways to combine the XY plane, the YZ plane, and the XZ plane. We have 3 of those orbitals. And I want you to notice that X times Y oscillation is over there. It's a second order combination. You see it in the character table. That's also a Raman active mode and vibration. What if we had a molecule that, let's do platinum chloride, PT, Cl, 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 Cl. And for some reason, we define the XY axis like this. So X and Y. And so we had this bond stretch out, and this bond compress, and this bond stretch out, and this bond compress. That stretching motion would also be X times Y. Now, if that messed with your brain, forget about it. But you can have vibrations be XY. You can have oscillations of the d orbital be XY. There's a lot of combinations where we can be XY. Okay, what about the X squared, Y squared? So this one, see, these three are the same, right? They're XY, XZ, YZ. But this one's different. It looks the same, but look at these. They go along the axis. And so if I squared the y-axis, all of the values would be positive. Okay, so the negative y is positive and the positive y is positive. Okay, so that's one color. What if I actually let me square the x. So let me erase those, just so it matches what the little designation is. So if I square the x-axis, I get positive here, and the negative x-axis gets positive as well because it's squared. And then if I square the y-axis, all of those things become positive, but if I subtract them from the x-axis, they become negative. And so this is the minus y squared part. It'd be negative, the deformation. Okay, so we have that same pattern, plus minus, only now those plus minuses go right along the x-axis and the y-axis. And then this one, I've got 2z squared, so z squared, again, positive here, deformation, and positive deformation down there, minus x squared, so all of the x values are negative, and minus y squared, so all of the y values are negative. And so those are all negative here, and there's no difference between x and y, so they're all merged together. So that's this shape. It's actually the 2z squared, which is positive, minus the x minus the y, so that's negative. And remember, we're not talking about charge. We're talking about deformation of the cloud. And so this one's bulging along the z-axis while it shrinks around the waist, and then it's bulging at the waist while it shrinks on the z-axis. So that's what's going on. Again, the dz squared, x squared, y squared orbital is going along the z-axis and shrinking along the xy and vice versa. And then the x squared minus y squared has nothing to do with z, but is expanding along the x-axis while it shrinks on the y, and then expanding along the y-axis while it shrinks on the x. Notice how both of those orbitals go along the axes, and so they are going to be things that bond with or interact with stuff on the axes, and the xy, xz, yz go between the axes. Okay. So those are the quantum numbers. Here's the d orbitals, the f orbitals, the g orbitals, and then we'll be done. So notice how the shapes get more and more complex. Notice how they're not very spherical at the p orbital or the d orbital, but as you get higher and higher in angular momentum, they kind of become spherical again. And so this is, again, that they become sort of the classical model of the electron can be everywhere the higher you go in angular momentum. This is just some extra information about the Zeeman effect and the Stark effect. The magnetic field is the Zeeman effect. This is how you can split the orbitals and know more about them. And then this spin-orbit coupling we'll get into later. So yeah, we're gonna have to start. We'll start here next time, the hydrogenic energy levels.